All right, let's do a big limiting reactant calculation here. These are fun. At least I hope it's fun. It should be for you. We've got nitrogen gas being prepared by passing ammonia over solid copper to oxide. The other products are solid copper and water vapor. They give us the balanced equation, which is nice. That's normally the first step. I would need the balanced equation. I need to know those ratios of reactants and products. Well, I'm not going to get this wrong because of the balanced equation, because that's given to me. I have 18.1 grams of ammonia reacting with 90.4 grams of copper oxide. I want to know how many grams of nitrogen can be formed and how many grams of the excess are left over. All right, so first thing we need to do is figure out the limiting and the excess reactant. Are these amounts the perfect stoichiometric ratio? Maybe they are, maybe they're not. But if they're not, I need to use the limiting reactant to determine the amount of nitrogen formed. So my first step is to look at these masses. Sometimes rookies will just look at that 90.4 grams of copper oxide and say, well, by far that's got to be excess. Well, number one, you can't compare grams. Ammonia and copper oxide will have very different molar masses. Number two, you don't know what the ratio is in the balanced equation. If I check this one, it's a 3-to-2 ratio. I'm supposed to have more copper oxide, but that's not a ratio of grams. It's a ratio of moles. So often our initial data is given to us in grams. That's how we measure in the lab. But we need to switch it to moles. 90.4 grams of that copper oxide. We need to compare these to that ratio in the balanced equation, but it's got to be in moles first. So I make one quick switch. Out of grams into moles. Oh, let's see here. Nitrogen, 14.01 plus 3 hydrogens. Gives me about 17.04. I don't need to show work for the molar masses, but I do need to show this step on calculating moles. Copper plus oxygen. 79.55. Plug these in my calculator. Maybe we'll leave 3 sig figs. 18.1 divided by 17.04. 1.06 moles of ammonia. And then I do the same thing with the copper oxide. Ooh, interesting. 1.14. So again, I just went to 3 sig figs. The masses were given in 3. All right, so I got these in moles, and now I notice that they're actually pretty close. The molar mass of copper oxide is so much larger than ammonia that, yeah, I mean, even though the masses are very different, it actually represents about the same amount of particles. However, I don't need the same amount of particles. I need more copper oxide, which I have. But this might be a good one where you'll say, ugh. Is that a 2-to-3 ratio? 3-to-2 ratio? I mean, yeah, it's more copper oxide, but that's kind of close to estimate. So then you pick one, either one. It really doesn't matter. What if, I don't know, for kicks you pick the 1.06 moles of ammonia? I don't know, it just came first. And we ask ourselves, let's say we want to use up all that ammonia. How much of the other reactant would I need? So we cancel the one that we picked, ammonia, and we switch it to the opposite. We plug in the ratio, 3-to-2. And I like this. Cancel my units just for fun. Okay, so we plug this in our calculator. We get about, 1.59. And again, you have to kind of think about what these numbers mean. What we calculated up here, these are amounts of moles that we have. We were given amounts in grams. We just switched them into moles. But this is my starting mixture. That's what I have. What I just calculated is the amount that I need. If I wanted to use up all the ammonia, I need 1.59 moles of copper oxide. We compare them in this order. What do you need versus what do you have? Interesting. We don't have enough. That copper oxide, that's your limiting reactant. Oh. So some people will be really quick to jump on this and be like, oh, it's probably the excess. There's like 90 grams of it. No, it's actually limiting. The excess will be the ammonia. This will be the ER. Okay, so we use the ratios from the balanced equation to determine the limiting reactant. And again, sometimes you can do that in your head. If this would have been an easy ratio, like a 1 to 2 or a 1 to 3, and maybe I had easy quantities that I could manipulate in my head, you might not be showing work. And if they ask you to justify your answer, maybe you just write a sentence and you say, well, it was a 1 to 2 ratio. I don't have twice as much, so that's my limiting reactant. This one, I wasn't sure, so I actually did plug this one on my calculator. And that work would be enough justification if they said justify my answer. Okay, so we got the limiting reactant. It's the copper oxide. That's the one that we use to determine the amount of product. So I'm going to go from copper oxide to nitrogen. I think that's what we're looking for. Yep. Okay, so I need to remember that ratio. 3 to 1. Now, you can take a little shortcut here. We started with 90.4 grams of copper oxide, and up here we turned it into moles. Well, when I do stoichiometry, I want to use that mole ratio. If you already calculated moles, you could start with this 1.14 moles of copper oxide. I mean, otherwise you got to go all the way back to 90.4 grams, and you're going to turn into moles anyway. So be resourceful if you'd like. And again, I always start with my limiting reactant. So now that I'm in moles right away, I can cancel moles of copper oxide and switch it over to whatever product I want. In this case, it's the nitrogen. My ratio is 1 to 3. You are gone, copper oxide. Okay, so right now I'd be at moles of nitrogen. And if I look at the problem, it does say how many grams of nitrogen. So we'll tack on one more. Cancel moles. We want grams. The nitrogen is diatomic in this equation, so it's got to be diatomic in my stoichiometry, which means the mass is going to be 28.02 instead of 14.01. Okay, so moles of nitrogen are gone, and I think we're ready. We can plug this all in our calculator. Let's leave 3 sig figs. That's what the original data had, and say about 10.6 grams of nitrogen. 10.6 grams of nitrogen formed. Not bad. Sometimes this really isn't a whole lot different than just a basic stoichiometry problem. You got to switch grams into moles for both reactants given. But again, if you can quick and easy figure out the limiting reactant, then that's the one that you start with for your final stoichiometry. It's not always such a beast to do these limiting reactant problems, but you have to think a little bit through them. Which reactant should I start with? Well, the one that runs out first. Okay, so the other part of this, they wanted to know how much of the excess is left over. Okay, the excess was the ammonia. So first we need to figure out how much of the excess was used. That's dependent on the limiting reactant. So I'm going to do almost the same thing. 1.14 moles of copper oxide, the limiting reactant. But this time, we'll cancel the limiting copper oxide, and we'll switch it over to the excess. This was my excess reactant. The ammonia. We'll plug in the ratio from the balanced equation. 2 to 3. And if you want, you can make a pit stop right here at moles. You can plug this in. 0.760. That's moles of ammonia that gets reacted or used. Thinking. Moles of ammonia used or reacted. Now, some people like to switch this into grams, and that would be totally fine too. Eventually, the problem does ask for grams, but you can do this kind of in either order. You can keep it in moles now, switch it to grams later, or you could go to grams now and moles later if you want to. Now we do a little comparison. What do we have versus how much was used or reacted? So if I go back to my original mole calculation, I have 1.06 moles of ammonia. That was from the original, was it 18.1? But then we switched it into moles. We'll just do a subtraction now. What we have minus the amount that was used or reacted. And if I keep it in moles, it was 0.760. The difference is the amount, that's an E, left over. Well, that's not so bad. It's about 0.3. 0.30 moles of ammonia excess. Now, you could have also done this in grams. In part 5, I could have switched that 0.76 moles of ammonia into grams of ammonia, and then I could subtracted it from 18.1 and be done. Or you can subtract in moles, and now we just have to switch it back to grams. 0.30 moles of ammonia. And then we just got to switch that guy out of moles into grams. The original molar mass that I used was, I believe, 17.04 grams per mole. Notice, too, when I did that subtraction, I only left 2 decimal spots. When you subtract, you normally leave the least amount of decimal places. So if you had gotten, some other kind of numbers that were hard to manipulate, you can always subtract and leave the amount of decimal spots in whatever number has less. And then now that's going to leave me 2 sig figs in my final answer, which is fine. We'll say 0.30 times 17.04. And we'll leave this as 5.1 grams of ammonia excess. Nice. I like that. All right, so the last part of this, we have to figure out how much of the excess gets used, and we just subtract it from the amount that we originally had. Eventually, I have to switch it to moles. Whether you do that in step 5 or 6 makes absolutely no difference. So hopefully this, too, is something that comes back to you. It rings a bell, because it's nothing beyond what you did in first year chem.